Greetings everyone, Professor Simon here. Let's get on with limits part 2. So we left off talking about a way that we could analyze limits numerically, and we went through several examples of that. Now what I want to do is expand the language that we're using just a little bit more into some of the pieces that we need every now and then. And that is being able to talk about the limits from one side or another only. Okay? When we were talking about limits before, it was a generic, everybody come together from all directions sort of idea. But limits can be thought of as singular patterns from one direction or another. And we just need a way to symbolize that. Okay? So one-sided limits is just another limit where I'm restricting myself to only coming from one direction instead. Whenever you want to come from the left, you'll see a little minus sign. It'll look kind of like an exponent on the number in the limiting process there. As x approaches 2 from the left is the way you read that when you see that little minus sign. Okay? And then x approaches 2 from the right when it has the little plus sign above it right there. And again, it looks like a little exponent. It's just an extra little symbol there to symbolize when it's from the left or from the right only. And then, like we saw before, if it's just as x approaches 2 inside of your limit, well then it's your normal everyday limit from all directions. Okay? So I can have this symbol in here and get one answer from the left. I can have a completely different answer when I symbolize from the right. Here's the example, right? One of the last examples that we did in the previous lecture was this function here. And I showed you how from one direction it was a -1, and from the other direction it was a +1. And we already determined that that meant that you couldn't say where the limit was. Okay? All right, so now what we have is the language to be able to describe that without having to go all say, oh, the gossip doesn't match or the patterns don't match. You can simply say this. A limit doesn't exist unless the left and right side limits are equal. Okay, so like in this example right here, the limit as x approaches 2 from the left is -1. And the limit as x approaches 2 from the right is +1. Since these are not equal, then the limit itself, no directional, is undefined. Okay? Here's another example. Imagine this function right here, 2 minus x, whenever x is less than 1, and 2x plus 1 whenever x is greater than or equal to 1. Okay, so piecewise function. We saw one of those last time too, right? And the one we did last time, the two pieces met up. Well, if you look, I've graphed this one out for you. You'll notice this time the two pieces do not meet up. But now we're armed with the language to discuss this without having to say all of those words like, you know, they don't meet up and the pieces are ones on the left and ones on the right, things like that. Okay? We have the limiting language here. I can say the limit as x approaches 1. Now remember, I picked 1 because that's the splitting x value here. That's the only interesting x value for this function. Okay, so limit as x approaches 1 from the left of f of x. Okay, so this is the whole function. Is the same thing as the limit as x approaches 1 from the left of the left-handed piece. See, I just picked 2 minus x here for this one because x is less than 1. That's left-hand side of 1. So I'll only be picking that piece. Okay? So when I numerically evaluate x from the left of 1, notice 0.7, 0.8, 0.9, 0.99, I'm approaching 1 from the left, from this side. Right? So I'm up in this region right here. Okay, and as I'm doing that, the 1.3, 1.2, 1.1, 1.01, that's me walking down this line right here, right? That's me walking down that line. So I can easily say that I can see that this is slowly and steadily approaching 1. Because notice every time I go up some 9s, I get some more zeros in between here. Okay? So the value of the left-handed limit is 1. All right? Next, limit as x approaches 1 from the right of the function f. Notice all I need to do is pick the 2x plus 1 because that's the piece that is dictated to be greater than 1 in the decision column here. So that's the only piece that I would be using to calculate on the right side of 1 anyway, right? So as x approaches 1 from the right, and then it's just of that piece. So again, from the right, I counted it down, 1.3, 1.2, 1.1, 1.01. I'm getting closer to 1 in the x values, as this thing says it should be. Notice I get 3.6, 3.4, 3.2, 3.02. I'm sure the more I go, I would just be getting more and more zeros here. As you can see, the value of the right-sided limit here is 3, right, from the numbers. But look, it's on the graph too. You can see from the right would be down this piece right here. And as I get closer, it wants to land right here. When x is 1, it wants to land right here at 3. You see? Right here at 3. Okay? So, the left-handed limit of the function as x gets to 1 is 1. And the right-handed limit of this function as x approaches 1 is 3. They don't agree. So overall, just the limit as x approaches 1 of f of x is undefined. Okay? All of the other limits that we computed, go back to the last section and take a quick look. I had the chart for both sides, right? I just did it as one big chart. But really, if you look at it closely, I was doing 2 different patterns, one from the left and one from the right. So we already were doing this. Now I've just given you the language, the symbols that we can use to communicate these ideas. Okay? Sometimes we only want to talk about a limit from just one side or another. And now we have the language to do that. Okay? Let's use a little bit of this language with the graphical version of finding the values for these limits. I have up here some graphs that from your previous math classes you should be able to graph using basic transformation and parent function knowledge. If you're not familiar with these graphs, that's okay, but you definitely should go look these up. If you want to, press pause right now on this and make sure you go and look up all of your basic parent functions like x squared, x cubed, absolute value, square root, ln of x, e to the x, right? 1 over x squared. These shapes should all look familiar to you. If not, then you probably want to just go get a quick refresher because these graphs are going to come up a lot in calculus. We study functions. Functions bring graphs with them. You need to know these. Okay? So let's do some of these limits using graphs. I see my function here is the quantity of x minus 3 all squared plus 1. X squared is a parabola shape. The minus 3 is a shift to the right. The plus 1 is a shift up. So I'm shifting it right and up. As you can see, my little center vertex there is at the coordinates 3, 1. Okay? So from the left-hand side, okay, from the left-hand side, that's going to be this. That's the left-hand side. Looks to me like as I let x move from the left, the y value is going to hit 1. So I put 1. Okay? From the right, that means I'm going to be following this piece of the graph, which gets me to this same center point, which again looks like it's hitting at the y value of 1. Okay? So since the left and right side patterns both equal 1, they agree at 1, I can then say the limit of x minus 3 all squared plus 1 is equal to 1. Okay? Now just because I don't get, sometimes I'll get a limit that's undefined, doesn't mean I still can't talk about the individual ones. In this case, since they both agree and I can get the full limit, right, and actually get this at the limit is, then this is the one I'll generally talk about, right? Because this being that one means they're both that anyway. Here's a good example though. The square root function, remember, is a sideways parabola, but it's only the top half because we made it into a function by only using the positive version of the square root, the top half. Okay? Well, it starts at the point 0, 0 here and then goes off to the right. There's no graph on the left part of the graph there. So when I ask you what's the limit as x approaches 0 from the left, that's me asking about, hey, what's going on over here? What's going on over here? Nothing. There's no graph over there. You can look at all the x values all you want. There's no y values to be measured. There's no people over there to gossip. For the big gossiping, remember limits of big gossip, right? So this is actually undefined. Because the function is undefined over there completely. It's missing all the points. Okay? Then the limit from the right would be this. I'll be coming from this direction. And it looks like as x approaches 0, right? So I'm going to get close to this point here. As x approaches 0, it looks like the y value wants to go to the origin. So this would be 0. Okay? If I wanted to talk about the limit altogether as x approaches 0, I'd have to say, there isn't one, right? Because the left-hand side doesn't exist. In a case like this, I would only bring up the limit as x approaches 0 from the right, because there is no left in the graph that even exists. Another example of the same thing, ln, right? Remember, ln is the shape here, right? It hugs the axis, the y-axis here, as x gets close to 0. But again, there's no graph on this side. Logarithms crank out imaginary values just like square roots do when you start plugging in negatives. So that's not something that appears on this graph. There are no function values on that side. So yet again, the limit as x approaches 0 from the left of ln of x is undefined. Whereas if I were to watch the values here coming from the right, if I'm coming from the right, I'm doing this. It's going this way, it's going this way, and then it's going to keep going down forever. It never actually hits this 0. But remember, that's where limits really shine. Limits have the ability to use infinities either as inputs or outputs without messing up any of our mathematical language, right? This limit right here is going to negative infinity as x approaches 0 from the right-hand side. As x approaches 0 from the right-hand side is doing this, the graph is doing this as it does that, right? It's going down forever and it never actually hits that axis. The limit is saying that it would get to negative infinity, right? If you could ever reach that point. If you could ever hit the axis, you'd be at a negative infinity there. Okay? So talking about how limits can use infinities as either inputs or outputs here, here's another good example. 1 over x, the reciprocal function. It's actually what we call a hyperbola. That's the shape that this breaks into. And what's happening is you can't divide by 0. So this is one of those big jokes and arguments out there where 1 divided by 0 is infinity. And really, in math, you got to be careful of your language, especially when it comes to infinities, right? 1 divided by 0 is not necessarily infinity, okay? And this limit right here will definitely demonstrate to you, that one and the next one, how you can get different answers with similar types of questions. Okay? So right here, if I approach 1 over x, if I approach 0, from the left-hand side in 1 over x, okay? That's along this piece of the graph here, okay? Or if you want to chart it out, think about it. I can put in anything to the left of 0 is going to be a negative number, right? So it makes the calculation negative. And the smaller that x gets, the larger the value is going to get. 1 over 2 is just a half, right? But 1 over 1 would be 1, 1 over 10, 1 over 100, right? I'm sorry, not 1 over 10 and 100. 1 over 1 over 0.5 would be 2. 1 over 0.1 would be 10. 1 over 0.0001 would be 1,000, right? 0.0001 would be 10,000. I'm sorry. Yeah, so my point is, the closer I get to 0, the more this is going to drop on the left-hand side. From the left, this limit goes to negative infinity, as you can see in the graph here. Okay? From the right, I'm plugging in nothing but positive numbers, but the numbers are getting smaller and smaller. 1 over 2, 1 over 1, 1 over 0.5, 1 over 0.1, 1 over 0.01. Okay? And what's happening is the closer I get to 0, right? Because here's x equals 0. The closer I get there, the more I have to ride up this curve. And it's going to go up to infinity this time. So altogether, you see the left and the right-hand sides don't agree. And therefore, I have to put undefined here. Although sometimes there are some people that will argue that the value of this limit itself is undefined, because infinity is not a value. And this is one of the great things that I love about limits. It's language, not just math. Okay? What is the tendency of the function if I let x do this, right? So this answer right here can be more than just a number. It can be an expression of a pattern or a direction or something like that. Okay? It's okay to put negative infinity and infinity for these kinds of answers, because yet again, these are not function values, they're not y values specifically, they're tendencies of what a function looks like it's going to do. Okay? So look at this one now. 1 over x squared, the reciprocal square function. I call it the volcano function, right? Look at the shape. From the left, you can see as x gets closer to 0 from the left, this curve just follows up this way, up to infinity. From the right, very similarly, right? I get closer to 0, I'm doing this. So that means I have to ride up this curve this way, like that. Okay? So I'm getting infinity for both of these. So what do you think the answer is over here? They agree, right? So we say infinity. Again, some people may argue undefined or just undefinable. I'm not using the limits to give a numerical answer necessarily. Limits are language. I am describing that this function from both sides goes unboundedly increasing forever as x approaches 0 in all directions. Okay? So this one right here is one of those ones that they would say, oh, 1 divided by 0, right, is infinity. But not always, right? 1 divided by 0 from one direction could give me negative infinity if I only count one direction. Also, there are other functions that you could do that are, slightly more complicated than this, where the infinities would happen faster or slower, or just if you have a mismatch of pieces from the left and the right, one of them can get to be infinity too fast, and then they don't agree anyway. I mean, if someone says, a solid statement like division by 0 gives infinity, you got to watch out for that. Okay? You need something concrete to grab onto, like one of these limits, an actual measurement, something with language that can be discussed and conveyed, right? One more example here for these graphical ones. E to the x, exponential function. Okay? Here's another usage of infinity like we did last time. I'm just doing the graphical side this time. As x approaches negative infinity. Now this is still a one-sided limit. Okay? I just don't need to signify from the right only, because there's no other way for x to approach negative infinity but from the right, moving to the left. See, because negative infinity is over on that side of the graph. I'm going to be moving from the right to get to it. That's the only way you can do it, right? Just like right here, x approaches infinity, that's going to be from the left only, because infinity is on that side of the number line. It's as far as you can imagine, right? So I'm going to be moving from the left. So you don't actually need to put the little symbols from the left, from the right on these things, okay? They're already implied, but they're still only one-sided limits. You only need one pattern, okay? So negative infinity would be letting x go this way, and so I have to follow the graph, right, this way. And it's getting closer and closer and closer there. So I'm actually getting 0, right? And then as x approaches infinity, x is going to go this way. On this side, the exponential function is completely unbounded. So of course here I'd have to give infinity. Okay? So a little bit of using graphs to do limits there, and our language with left and right-sided limits. Let's finish up this discussion on the second part of limits by using this further language that I've shown you to define something that you've been using since your earlier algebra days and have just been sort of hand-wavingly told you what they mean. I'm talking about asymptotes. Usually in an algebra class, and I'm going to do this all the time too, for the algebra students, we just say these asymptotes are these lines that you can never touch, but you try to anyway, right? It's these lovely magical objects that help us understand the shape and stuff like that. Now it's time for us to give rigorous definitions for vertical and horizontal asymptotes, because now we have the language to do that. Really, vertical and horizontal asymptotes don't exist, which is sort of what we tell you in algebra. But the idea that they don't exist means that they're not actually objects that are part of your graph. It means it's a human way for us to understand a pattern that we can't necessarily see right away. And we just are told when to look out for these particular asymptotes, special magical objects, okay? But if we give them actual definitions with real mathematical language, then we know when to look for them ourselves, and when we can actually define them and when not, okay? So here we go. A vertical asymptote. Anytime you have a limit from one side or another of some number, so if x approaches c from the left or x approaches c from the right, if the answer from either one of those directions, typically both, but sometimes you can have just one-sided, like the example we had earlier with the ln, right? It was only on the right-hand side, okay? All it takes is one of the sides to go off to either positive or negative infinity, okay? The limit language would say the limit is equal to infinity, meaning the function is increasing without bound as you try to approach that particular x value. Either direction is all it takes. Then by this definition, we're saying that that particular x value is a vertical asymptote. So the object x equals c, we typically graph those as vertical lines, is a vertical asymptote. But in this case, it's the x value itself that we're calling the asymptote here, because it's a particular limiting approach that causes the infinite limit value. So that's what the asymptote really is. It's that particular x value, Okay? When we're drawing the graph, we draw the vertical asymptote as a vertical line. Really, that's just something to help us visually understand the pattern that's going on with the function itself. So then, vice versa. If I do a limit as x approaches negative infinity, right, which is a limit only from the right, or a limit as x approaches positive infinity, which is a limit only from the left in that direction, and you actually get a numerical value instead of some sort of infinity or unbounded pattern, okay? So if I actually get a numerical answer for either one of these limits, then that particular y value, that limiting answer, is a y value now because it's a number. Y equal to that number becomes a horizontal asymptote, and it could be just a one-sided horizontal asymptote. For example, the one we saw here, limit as x goes to negative infinity of e to the x, is only on the left-hand side. It's only on that negative infinity portion of the graph because e to the x on the other side is unbounded. Okay? Still, y equals 0 is a horizontal asymptote for this function. Okay? Again, it's the y value now that you can see is that limiting answer value as x struggles really hard to try and get to this infinite value that it will never reach. The pattern that we need to visually see is us drawing this horizontal line, right? That's how we visualize it. But the horizontal asymptote itself is this y value that's an answer to this limiting pattern, okay? So let's get a few examples of some things that will come up all the time when we're graphing. We're going to be doing limits, we're going to be doing derivatives right after, and then when we apply derivatives later, we're going to do curve sketching. So don't just brush this off. These limits are going to come up again in the next couple of chapters when we start bringing everything together and using all of our calculus knowledge to draw very accurate graphs and curve sketching. Okay, so this is sort of like warning in stage number 1. Limits are very useful language when you want to either investigate, analyze, or communicate a function. Okay, so here's one of the ways limits help us describe that language. If I have this rational function, 3x squared plus 1 over 5x squared plus 2. In algebra, you would have been told to look at this rational function and decide, since the exponents on the top and bottom are the same, I can do that type 2 horizontal asymptote that Mr. Simon showed me the little quick rule for. And I can tell you that since they're tied, it's the struggle between 3 and 5, so it's 3/5. Boom, got my horizontal asymptote. Great. Is that the way it's really supposed to be done? No. But we don't do limits in college algebra. Now we are. Let's use the proper language. If I take the limit as x goes to infinity of this function, right? So I'm doing that. I'm counting my patterns as x goes to infinity. And every time I put another 0 behind that, 1, 10, 100, 1,000, 10,000, every time I put another 0, I change from a fraction to the next size fraction up where there's another 0 in there. So 4/5, that's really 3 plus 1, right? Oops, that shouldn't be fifths. That should be sevenths. Sevenths. Okay, so 4/7 is really 3 plus 1 and 5 plus 2. But every time I add that 0, right, I get 301, 502. 300,001, 500,002. Okay, so on and so on. You see, you just get more and more zeros between the 3 and the 1 and between the 5 and the 2 in your fraction. And the further those zeros push away, the 3 and the 5 becomes so much bigger than that 1 and 2 on the end of your fraction there. So really you can see it. It's becoming 3/5 the more zeros you stuff in between the numerals and the numerator denominator there. So I'm getting 3/5 as an answer to this limit. The exact same thing happens on the negative side. If I let x go to negative infinity, okay? Even though I'm plugging in negative numbers, the squares knock the negatives away. Although in the case of the even without the squares, if they were both x to the 1, negative over negative would be positive and it would still work out. Okay? The exact same thing size-wise is happening. 4 sevenths, 301, 502, 300,001, 500,002. The more zeros is the more stuffing that you have in between those digits. And you can see the 3/5 literally just fall right out of that pattern. So this is how we discuss that pattern, right? The limit as x goes to negative infinity of the function is 3/5. So by definition, y equals 3/5 is a horizontal asymptote on both sides for this function. Okay? Here's another example from trigonometry. Secant x. That's the graph where if you were to draw cosine, right? Cosine is the graph that it peaks out like this. Right? Looks like this. That would be cosine. Secant is the reciprocal, one that fits in around the cosine, but secant has asymptotes. Why? Why does it have asymptotes? Because of division by 0. Well, the 1 over the cosine, the reciprocal there, is what causes it. So let's pick off those values, right? If I take the limit as x goes to pi over 2 from the left, what I'm actually doing is going up this curve right here. Okay, this piece of the curve right here. Because this line that I drew right here is pi over 2. This line right here. So as I go this way, as you can see what's happening, okay? Or in your calculator, pi over 2 is around 1.57-ish. Plug in secant of 1, secant of 1.2, secant of 1.5. Plug those in your calculator. You'll see the value just explode. But that's just from the left-hand side. Just the left-hand side, right? And that's what limit I have here. The answer is infinity. Okay? Now, what about x approaches 3 pi over 2 from the right? 3 pi over 2 is this next line over here. And I would be approaching it from the right. So that would be coming up this curve here, this red piece. Again, if you wanted to plug that into your calculator, 3 pi over 2 is around 4 point, let's see, let me double check, let me make sure I'm saying it right. Yeah, 4.7. Okay, so from the right, if you're approaching 4.71, start with 4.9, 4.8, 4.75. You keep plugging those into secant. You're going to see the value just explode in your chart. Again, this one's going to be positive because those numbers that you're plugging in are going to be quadrant 4 numbers, right? Cosine and secant are positive there. Same thing right here. You're plugging in quadrant 1 numbers. Are these the only 2 asymptotes for secant? No. There's actually an infinite number. Secant is a periodic function. It keeps repeating over and over and over again. These are just 2 examples. Okay? So with our language that we've written here, right, what can we say? X equals pi over 2 and 3 pi over 2 are vertical asymptotes for y equals secant x. Another one that comes up a lot in later sections that we do is the arctangent function. The arctangent function comes up quite a bit in some of our later integrals as well. This limiting value is going to come back. You need to remember this. This is basically the shape of a tangent curve, but remember normally tangent curves went this way, right? But they had vertical asymptotes. For arctangent, you're just taking one of those and inverting it. So I'm getting 2 horizontal asymptotes. This was an easy one to chart out though. Put your calculator in radians, right? And do secant tangent. Do inverse tangent of 100. Do inverse tangent of 1,000. Do inverse tangent of 1,000,000. Okay? And let's see what you get. inverse tangent in radians of 1,000,000. 1.57. Wait a minute, that number should sound familiar. 1.57. We were just talking about that one, right? It's pi over 2. And that's exactly what this is. The larger I let x go to positive, I plugged in 1,000,000, right? If I typed in 1,000,000,000, it would be 1.571. It would be even closer, okay? As x goes to infinity here, this line is represented by pi over 2. Do the same thing. As x goes to negative infinity, the inverse tangent of a negative number is going to give you a negative number. So if I put in negative 1,000,000, inverse tangent, negative 1,000,000, I would get negative 1.57. So what does that mean? It's negative pi over 2. Okay? This is just us using our language now to describe what's going on in these functions. But also, since this limit as x goes to negative infinity actually gives me a numerical answer, a non-infinite answer, same thing here, I can actually write these as horizontal asymptotes. Y equals negative pi over 2 and y equals pi over 2 are horizontal asymptotes for arctangent of x. Okay? Don't just take my word for it. Let me show you these real quick in GeoGebra. Okay? After that, I hope all of this has helped you understand limits even a little bit more. Stay tuned for limits part 3, where we start talking about how to evaluate these things quicker and more efficiently. I wanted to show you those last 3 graphs here so that you could get the visual side of those limits and asymptotes. Let's take a look at that first one. Y equals 3x squared plus 1 over 5x squared plus 2. You can't really get much out of this. It almost looks like a horizontal line. But watch, if I extend this a good bit, right, you can see that it does actually have some curve in the actual function there. But it only stretches between the 0.5 and the 0.6 here, right? So what we're looking at is, if I were to type in y equals 3/5, by the way, that's 0.6, you'll notice that the line that we get there, the horizontal line, what we would normally call the horizontal asymptote, right, is this horizontal line. And you can see it is indeed hugging it like so, and almost becoming one with it as x goes off to both negative infinity and positive infinity. So that's what that graph looks like. It's very, very tiny. Okay, so the next one that we were talking about was the secant function. Let's move that up and over right here. Let's get our grid back. Okay. So then our secant function looks like this. Remember, it's the function that cosine can fit in between. Right? That's what cosine would look like if I were to graph it. Because the secant and the cosine are reciprocals. But cosine isn't what we're studying here with this limit. The secant is. So let's look at secant. And notice these are the two vertical asymptotes that we talked about there. Pi over 2 from the left is this guy right here. And you can see it does go off to infinity. It does try to hug that line there. Same thing right here. X approaches 3 pi over 2 from the right, is right here. And as you can tell, there's more and more and more of these vertical asymptotes, right? In between each one of these things would technically be one. There's an infinite number of these things. Lastly, the arctangent, the inverse tangent, looks like this. It's basically just an inverted tangent wave, but only one of them.
And it is fully trapped between the y values of pi over 2 and negative pi over 2, as you can see. That's the equation here. It does actually hug those lines. If you let x go really, really far out, you can see it starts to really hug them really, really tightly there. So those are horizontal asymptotes for the arctangent.